Hello and welcome to a lecture on the LibreSOC project, and the core of this material will cover the differences between developing something for an FPGA and developing it for an ASIC, and how to go about being able to target both. We can also target simulations in several different ways, but that's out of scope for this particular course. So a bit of background: this is our project. It's our main website. It's a wiki. It's editable. We're a Libre project. Okay, and that has very specific meanings. It means the majority of open projects, they will throw the code only when it's ready and when it's done. Libre, everything is transparent. We make all source code, all technical discussions about that source code are entirely public and real time. Also, there are ethical guarantees behind Libre where open is considered unethical because there is no requirement that people who use it actually contribute back the modifications and enhancements that they need to do, whereas Libre requires that you contribute back those modifications. So on the sidebar here you can see there is a number of resources, including our charter, links to the mailing list and archives, etc., etc. Now let's go first of all over the LibreSOC Core itself, and then expand out from there. So what we have is we are running a very simple finite state machine. It is not a pipelined design, and the reason for this is because it can be used as an exercise, an academic exercise, because it's very straightforward and easy to see how it works. When you get into pipelining, it becomes extremely complex. The overlaps just you have to know a lot about the internals, etc., etc. So what we did was we went through the standard fetch, decode, issue, and execute phases, but did so one cycle at a time. So pipelines, they will run them, that will run all of those in overlaps. Whereas this, it does a fetch stage, waits for that to complete, then passes the instruction that is fetched to the decode phase, waits for that to complete. On decode, it's been able to identify what the instruction is, so it can then read the registers that are needed here. It then passes those to a pipeline. Now we have multiple satellite pipelines. It's not just one pipeline in the LibreSOC design. There's actually 12 separate pipelines because we're planning ahead for an advanced design. And there again, it waits for the execution to complete, and then that's followed up by writing the results to register files. And then in an intrusive fashion, what we do is we detect if the program counter was written to by the previous by one of the pipelines, and if it was not written to, then the issuer finite state machine will increment the program counter and store that in the register file. But it also detects the MSR register, which is part of the power instruction set, and there is a separate pipeline finite state machine for updating the DEC and the TB register, which are timer and decrement registers. Now, and then it goes back and does it all again. Now, a little bit more detail going over that thing. the program gather fetch phase of the finite state machine will fetch over the instruction wishbone bus. Okay. At the decode phase, we have a class, a Python class called Power Decoder. Sorry, Power Decoder 2. By the way, all of this is written in Namigen. Namigen outputs Verilog. There's a very specific reason for doing it that way and using Namigen rather than Verilog, because Verilog is 1990s technology. You cannot do classes, you cannot do properly do interfaces, and it creates unwieldy, unmanageable code. We therefore consider Verilog to be a machine code target. Right, and that's how Namigen works. So the Power Decoder 2 will actually decode the binary instruction, but it also receives the interrupt lines, external interrupt and other interrupt sources. And on the basis that when a interrupt occurs, you need to execute an interrupt. You need to carry out changes to the program counter. You need to thing, and it turns out that this is basically the equivalent to trap. So what we've done is, in a microcode form, is simply overloaded the trap mechanism to make it look like we're executing an instruction, and that instruction updates and replaces the program counter and the MSR, and stores the old copies of those in SRR0 and SRR1. Right? But it's done by getting the Power Decoder to go, oh, there was an interrupt. I'm going to ignore the current instruction that came in for the decode phase. I'm going to issue a trap instruction, aka interrupt micro-coded instruction instead. Then, having decoded that instruction, you go for you can know what registers would need to be read, and we have a lot of separate register files: integer condition register, SPR slow, state fast, and a fast SPR register file, which is very, very small and has massive number of write ports, read and write ports. But it's very small, and it contains link register, tar register, couple of others, which are needed for high-speed access. And there's a separate XER register, and that's merged into the SPRs when it's read. And Microwatt does exactly the same thing here. So having read all the registers, then go into the pipeline execute phase. Now here what we've got, because we have multiple pipelines, we also have multiple satellite power decoder 2 instances. And these, thanks to using Python, we can subset those by the fields that are needed in the columns and subdivide them for the rows, because at the back at here at the main decoder, the main decoder decodes every instruction, but it only decodes enough information on how to identify the registers to be read, the register to be write, and the pipeline to which the instructions should be farmed. Now that leaves more information in the instruction which needs to be decoded, but it could be done in a satellite form at the source just right before the actual instruction. So standard pipeline thing, the instruction goes through it, blah, blah, blah. You get a notification back that the output is available, and that goes into the register write thing. And again, it's exactly the same as the read reg files. It's the same thing. All right. Now, I'll show you the source code for this later and link you to it. Now, in addition to that, in the same class, there is a Debug DMI interface, which is mirrored on the RISC-V DMI concept and conforms to the same API. But it's actually implemented in microwatt. The microwatt decided to do their own DMI addressing system, so we just copy that and we're fully compatible with it. Now, this manages the core, and it's fronted by a JTAG tap interface. So there's an adapter from JTAG to debug, which is not part of the actual core itself, but it's just a front. And through the DMI interface, what the microwatt team did was they defined some registers. So that when you poke the particular address, it means it gives you some bits which indicate please start, or please stop, or please reset the core. So over that interface, we can send commands, and because it's linked to JTAG, we can send JTAG commands to start, stop, and reset the core. And that hooks into the finite state machine here. So you send the command over DMI, and it acknowledges immediately. But of course, you cut the finite state machine. The actual execution is in the middle of executing things, so it can only just, what you have to do is wait, and you get some information back. Which you have to make another DMI request to say, have you stopped? What is your status? And you'll be able to check it if it's stopping and if it's stopped. All right. So again, over this DMI interface, you've got PC update and read, and you have register read. So you have yet more ports into the reg files here. The one thing that I've missed to say is that the Loadstore Pipeline is what accesses the Wishbone data bus. Okay, right. So there's these two Wishbone masters. One is the instruction Wishbone master and the data Wishbone master. The actual core itself does not get involved at all with Loadstore accesses. It's handled entirely right down at the end of the pipeline. So with that in mind as what the actual core is, we can now move to where the interface is. Here's what the contents of that previous slide was, with the previous diagram was with the test issuer. So you can see the instruction Wishbone bus is input and output from it. The data Wishbone master is on here. We have interrupt lines coming in, which go into the ZIX controller, which has a ICP presentation layer, interrupt controller presentation, and interrupt controller session layer. But it becomes a definition of what the interfaces are for test issuer. And we have the DMI interface. Right. So then there's also those pipelines and registers, and also the actual decoders, the main decoder and the satellite decoder. So as far as everything else is concerned, you see basically these four sets of wires: the DMI, which includes everything for JTAG, the interrupts, and the Wishbone bus. You see nothing else, literally nothing else. You don't see the registers because that's handled through the DMI. You don't see any pipelines or anything like that. So this is just these four interfaces. Now, on the other side, we have the JTAG tap. Right. Now this is a standard 4-pin interface, and what Chips for Makers has designed into the JTAG tap interface on Namigen, written in Namigen, is the ability to add a Wishbone master. We also added the ability to add a DMI interface, and there's also a standard boundary scan system. Right. Now, most FPGA open source code does not have boundary scan. Why would you need it? And the reason why you won't need it is because you can very simply reconfigure your FPGA bit stream to use different pins. You just recompile the bit stream. Right, so this becomes one of the key differences between FPGA programming for FPGA and programming for ASICs. You have no idea if when you have an error. One of the crucial things to understand is that you need when you have a bug and you've basically got a black box. the last thing you want is more than one thing that that could possibly be a failure. And the reason for that is because if you make a test where that test is a single thing, success or fail, if there are two possible things that could have failed, you have four possible permutations, only one of which you can dictate when you get your black box outside success. One of those permutations will be because of the two failures, because of the two things. The other three possible permutations, you have no idea which one of those two things caused the failure. And so let us say that you have a failure in the core and you have a failure in the I/O pad. From the outside, you cannot get access through the JTAG interface to determine, I'm not getting response on this I/O pad. Why is that? Well, you don't know. It could be a failure in the core. It could be a failure in the I/O pad, and you cannot tell which it is. So by having a boundary scan and separating, you see this break here, you cut the entire core out of the equation and go directly to the I/O pads. And by going directly to the I/O pads, you are able to determine if it is the actual I/O pad, and then if that succeeds, then you go back to enabling the core, and you can, by logical deduction, if there is a fault and the I/O pads are okay, you know it was the core. But unless you have this the ability to directly test this one and one only one thing, you cannot determine which one it was. So so that's why why you have boundary scan. Now the reason why you don't have boundary scan in FPGAs is because you don't need it. You can just reprogram the FPGA to route the peripheral directly to the pads. And if it's not the right thing that you need at that particular time, just go back to the source code, reconfigure the source code, recompile the bit stream to connect different peripherals, and upload the new bit stream to the FPGA. Clearly, you cannot do that in an ASIC. So LiteX is actually configured. It's not configured to understand this concept because it has been designed exclusively for FPGAs. Consequently, we had to do a lot of hacking to get it to understand this the separation between the two, and I'll go over that later on. So whilst LiteX itself defines the peripherals, which by the way are nothing to do with the core itself. The core is just it does memory access only. It's memory map peripherals. So this is why you have to have memory map peripherals, because the only interfaces that the core understands is via memory and interrupts. Okay. So consequently, the peripherals must define their public interface as far as the core is concerned in terms of memory and interrupts. And on the other side will be the I/O pads that come out. So in the test chip LS180, we wanted to include SPI I2C, UART SDMMC, SDRAM, which is DDR1, is 133 MHz DDR1, GPIO, external interrupt, and PWM. But it turned out that we had too many resources, so we cut out many of these, but kept EINT, GPIO, SDRAM, UART, I2C, and one SPI master. Now, what they would then have to do is route those So LTX defines a set of pads that are normally connected directly to the FPGA resources, internal resources. We had to route those to the JTAG tap boundary scan. And the JTAG tap boundary scan to do a MUX switch that then either routes to the through to some internal registers which you can read or write to via JTAG, or if you flip the switch, the MUX reroutes it to the actual I/O pads that would normally LTX would connect directly to itself. Now, this a minor complication is that those the JTAG tap code is actually inside test issuer as one of its submodules. So for convenience, what I've done is I've written this diagram out in such a way that it appears as not quite the case that, but this component here is actually inside here. And what that means is that every single pin on here, defined by LTX, has to be on the public interface here, but it is not part of the actual core itself. The core only understands memory, wishbone, and interrupts. Okay? So, let's move on to what some of the differences are when you have between an FPGA and an ASIC. In any ASIC, you have LUT4s or sometimes LUT6s, and these are lookup tables, which are 4 input that can, depending on the permutations of the inputs, it will create via a lookup table, hence LUT, a combination of outputs. So if you have 4 inputs, you have a 16 entry state table, which creates, based on any of those possible combinations of the 4 inputs, will produce outputs. And this basically allows you to emulate, and I do mean emulate, XOR gates, MUX gates, NOT gates, NAND gates, AND gates, blah, blah, all the standard gate things. Now, one thing that LUT4s can't do is they can't be a BRAM, a block RAM. You also have DFFs, which are latches, and typically the more advanced FPGAs will also have a DSP. Right? And the DSP will have multiply and add, etc., because to implement multiply is a massive number of gates. And it's just a waste of resources, waste of LUT4s. You're better off doing it in a very efficient manner as a dedicated DSP block. And then you have GPIO of different types. Now, here we have one of the key things. GPIO, you basically reconfigurable GPIO. You have to have an input, you have to have an output, and you have to have an output enable. Now, I won't go into the differences about things like DDR pads and SerDes differential pair pads. Basically, they're exactly the same. They have an input and they have an output, and they have an output enable. And when you raise the output enable high, the pad becomes an output. When you raise it low, it becomes an input. Right. So here's the LibreSOC Core, and it's separate from that is the LTX Peripheral Generator, and the whole lot gets compiled to Verilog. There's one Verilog file for LibreSOC, one Verilog for the LTX Peripherals. They get thrown to the tools, and the tools generate the cells and the resources, generates a bit stream which will conform to the things and do everything that's needed, and that's handled by LiteX, but there's several other tools as well. NamiGen itself can actually target a huge number of FPGAs with the different platforms on which those appear. Now, and also in the FPGA you have a PLL block. Okay, now in an ASIC you get no assistance of any kind from any resources. You have to do everything yourself, right? So you have to have a PLL block, you have to have SRAM blocks, you have to have MUX blocks, you have to have a flip-flop block, a XOR block, a NAND block, a NOT block, a buffer block, a diode, everything. And these are called cells. And don't be confused by the term cell. It means any collection of gates. So there is even a LibreSOC cell, and it's 130,000 other cells which are laid out in gate level. There is a PLL cell, and that's about 10,000 transistors. A thing comprising some other cells. So please don't be confused when you see the concept of cell referring to something that's only got 5 transistors, and the exact same term referring to something that's got 500,000 or 1,000,000 transistors in it. Welcome to ASIC industry, ASIC VLSI industry. So there is also an IO pad cell, all right, which has to be provided. Now these are usually provided by the foundry, and the foundry puts you under NDA, which from an academic perspective prevents you and prohibits you from even being able to publish academic papers. Right, because you use some NDA material, you are prevented and prohibited from publishing. Isn't that wonderful? So this is why there is a huge amount of interest in NDA-free cell libraries and in NDA-free foundry process, in particular MOSIS. But MOSIS comes with some punishment in that it is double the size of the optimized cells that are non-NDA free, and only some foundries will refuse to accept MOSIS formatted GDS2 files. So you have to be, it's a tiptoeing nightmare, to be honest. One of the key things, so we have to have a PLL, we have to have an SRAM block or SRAM blocks, particularly for register files, for onboard memory, and all these cell libraries. Now we've I won't go into detail on that thing, but basically here you have all the resources on the FPGA side. You have all of these resources already done for you, your LUT4s, your BRAMs, etc. They're already laid out, and the FPGA, you are allowed to route that pre-existing fabric but through the bitstream. The bitstream gets uploaded and programs that routing. It's incredibly expensive in both area and power consumption, but it's reprogrammable. Whereas for the ASIC tools will actually lay out, and then you go and print it out, and you cannot change it after it's laid out, unless it's actually unless your ASIC is an implementation of an FPGA. It's quite funny. Now, the in, out, and output enable here, which in LiteX it gets connected as just a GPIO. Here, that triplet of in, out, and output enable per pin on your interface need to be passed right the way through the entire source code, entire netlist, until they hit the individual pad, IO cell, containing that in, out, and output enable. Right? And this makes for a very crucial thing, which LiteX doesn't actually support this, and we had to hack it into submission to get it to do so. In addition to that, we had to define a platform which had its own PLL, but as a black box cell. And likewise the SRAM. So in LiteX, if you have a look at the platform, the things, the LiteX platform code defines and understands the PLL block and wires it up for you, so that when the bitstream is programmed, it will go into it will enable and connect everything up. But here, because it's a PLL block, we need a .v file, which a Verilog module, which represents that, and LiteX needs to doesn't so much need to know about it as the LibreSOC code just needs to tell the VLSI tools about it as yet another cell. But in this particular case, because it was defined externally by a LIP6 team, and because Yosis doesn't understand it, we actually had to mark that PLL cell as a black box to Yosis to get it to not try and do some optimization, etc., etc. And likewise for the 4K SRAMs, of which we put 4 down. So you won't see a 4K SRAM in the FPGA, and you won't see a LibreSOC PLL in the FPGA, because we are using the existing PLL and the existing block RAM of the FPGA resources. Okay. So this is why LiteX here we couldn't, because of the JTAG boundary scan, we actually had to route the peripheral set out of LiteX into LibreSOC. LibreSOC handled the JTAG boundary scan muxing, then route it back into LiteX, and for LiteX to go and create the pin set. Remember this triple pad in and out and output enable for every single one of the pins. And finally, that will be passed to those Peripherals, one of the LibreSOC.v and LiteX LiteOx.v would be passed to the VLSI tools. So here's the workflow. I apologize, I've missed off the PLL.v and the 4K SRAM blackbox.v files. So at the top here, you've got the test issue where you've got JTAG tab with its JTAG tap interface with the DMI interface and the ZIX controller. That is then, because that is in Namigen, it is handed to Namigen compiler. Namigen compiles that to a Yosis RTLIL file, aka ilang file, intermediary language. Yosis then picks that back up and reads it in and converts it to Verilog, and then saves, and this is all under the control of Namigen. Namigen then saves that as a Verilog file, which we chose to call ls180.v. On the other side, you then run another makefile command, which runs LiteX to auto-generate the LiteX peripheral fabric interconnect. And that our use of LiteX has told it about the various interfaces, which we'll go over the source code in a bit, and that will generate a LibreSOC.v file again in Verilog. Now those two files are then handed through. So if you to the different workflow toolchain. So if you want to do FPGA, you run one command to build the FPGA bitstream, and if on the other hand, if you want to compile it to a GDS2 file, you hand it over to Coriolis2. Now. So let's say we go the FPGA route. We take the two Verilog files, ls180.v and LibreSOC.v, and through the LTX command line, behind the scenes it will run YOSYS to read those two files in and convert it's likely to a BLIF file or an ilang file, and then it will run next PNR ECP5. Now YOSYS is actually pre-programmed, built in to understand the ECP5 cell structure. These things here: how many LUT4s, how many BRAMs, how many DSP multiply slices, how much GPIO, where is it, what is it, how many PLLs it has, etc., etc. And so when next PNR receives the information about instructions, it will do a place and route, next PNR, place and route, and generate a bit stream, and that bit stream can then be uploaded to ECP5, and you've got a representation of your HDL, which actually runs at the gate on your FPGA. Taking the same route, going back to the ASIC, again, interestingly, it uses YOSYS thing, and this time it compiles to BLIF. And it is at this point, remember that YOSYS doesn't necessarily know about the geometry and the cell library, what the cells actually have. So you have to tell it. And in our case, what we've done is there's a couple of routes, but basically they both go something called Flexlib, which is by Chips for Makers, which contains the cells, and YOSYS is intelligent and general enough that when it's given those cells and told what the inputs and outputs are, it can actually do the mapping. It doesn't matter if you have a MUX4 or a MUX8 or a LUT4 or a LUT6 or a LUT8 or a buffer with this many. It's absolutely brilliant. It will just map your HDL down onto those cells. It's a cell mapper where a standard cell library happens to be a list of cells. So that outputs a BLIF file, which Leos and Coriolis 2 have been programmed to understand and read. Now, what Coriolis does it actually understands its internal data structures. It uses a subset of VHDL. So there is a BLF to VHD converter, which then it can be picked up again by the place and route program, which is controlled under the control of Python programs settings.py and dodesign.py as part of Coriolis 2. After the place and route, which takes over an hour to 90 minutes, you end up with a netlist, which again you can extract and end up with this VLL subset, but it will be at the gate level, or cell level of connections to the cells, and consequently that cell library is an important input into this phase here, which is where you pick up the logical representations of the cell library in either Verilog and it's Verilog or VHDL, and it's why you have those. So it will also it also will output a SPICE model, a SPICE netlist, the same thing. So it's really very, very convenient, and you get the GDS2 file. GDS2 file you send off to the foundry, and you get your chip back. Now, one thing I didn't mention here is that the LibreSOC 180 PenMarks is a crucial strategic part of this system. It's related to the peripherals. It actually ties in 3 or possibly even 4 different ways, and it's basically I'm slightly shocked and taken aback that in the standard industry practice you duplicate all of this information. But as a software engineer, that's completely insane. If you don't have an automated way to represent the pins of your peripherals, you end up duplicating that information. You make mistakes. You can potentially make mistakes. And if you want to make even one single change, which we actually did for the 180 nanometer layout, because we needed to move the power pads, you need to make changes in 4 separate places, but data going right back into your HDL and into the LTX peripherals and into the corona of the ASIC. So to avoid that insanity, what we did was we got this program, PenMarks program, which auto-generates a JSON file which every single one of these separate components, the Namidian HDL, the LTX peripherals, and the Coriolis 2 Corona generator can pick up and understand. All right. Incidentally, you can also generate Markdown files from the same output, and even we chose to generate a where is it? I'm jumping ahead here. Yes, here we go. We chose this diagram is auto-generated. I did not write this by hand. All of those pads on the output and the input were put on through a Python program which outputted an SVG diagram. Okay? That's the kind of thing that a software engineer would do, but a hardware engineer would not, because they've not trained. Hardware engineers are not trained in software engineering techniques. So, I'm just going to pause the recording now and bring something on screen externally, because I wanted to show you the differences between when you run Yosis on some HDL for an FPGA and when you run it for ASIC. So please let me just go off screen and pause this, and I'll be back in a second. Okay. So this is a diagram which a partitioned signal module which we're developing for LibreSOC to do automatic SIMD, and this is a Yosis show top command on one of the test benches, and you can see we've got modules here for there's a greater than or equal test as part of it, etc. And we can, if I do an additional command, show EQ_2, and we can see that this is doing a partitioned equal. All right, and there's another submodule here, greater than thing. All right, now. So bear in mind that these are high-level connections. This is a net list for the design. Show top. Now what we're going to do is we're going to do synth ECP5 return and show top. Yeah. Whoops, it's a big design, so it takes quite a lot. And let's. Here we go, and let's zoom in. Okay, so there's an output thing. These, I believe, are some of the LUT4 cells. Oh no, here we go. Here's your LUT4 cells. All right, okay. So it's turned it into a series of resources because Yosis contains an understanding built into the actual source code of Yosis. The lattice ECP5 cells, which we described on the other, on the previous diagrams, LUT4s, BRAMs, PLL things, MUX, DSP, mole slice, etc., things. So that's what you end up with there. So let's now load that in again. Control D, Yosis. Read idling that file, proc synth. So show top again. Let's have a look at that. Let's do also, we're back to that top level design there. And now I'm going to run proc and synth. No, I'm not going to do that. I'm going to do read-ilang and just plain synth. Now this will use a default standard cell library. And it's taking forever. Show. Okay, it's finished and it's done. Right, I didn't do flatten, so it will do it as show top. It will do it as a series of submodules. So I will need to do show add _1. And here we go. Because I used the standard cell library, it's now, instead of LUT4 and etc., it's assumed that we're using AND cells. And here's a MUX cell. So there's an AND, a NAND gate, an exclusive NOR cell, an OR cell, and so on and so forth. And so coming back to here, that's what we do is we hand it the Flexlib cell library, which contains the cells that have been designed by chips for makers, and those the Coriolis Yosis will then incorporate that and generate the BLF file from that cell library. Right? So it's quite it's really quite straightforward, but it's just that normally this cell library would be under NDA. You would not be permitted access to it, or you'd not be able to publish any academic work having signed such an NDA, which is accepted at a very high level. And consequently, there's been something called FreePDK 45 has been designed, which Flexlib has been ported to that, so you can actually compile to an academic use cell library. Now, there's no point in taping it out because it will be it contain nonsense. It's ghost cells, but you will actually be able to complete a GDS2 tape out using that academic ghost library. So with that so let's recap. So we went over what the LibreSOC Core contains. We described that it has these interfaces, which is memory, interrupts, and DMI only. That the JTAG tap is separate from that, but has a boundary scan and has its own wishbone master, which is completely separate from the test issuer instruction and data wishbone, so that the over the JTAG tap we can get direct access both to the 4K SRAMs and to the peripherals and test them independently of the core. Then we described some of the differences in the resources that are available within the within an FPGA and an ASIC. In particular, that you just don't have anything existing at all, but also that you have to have this in the GPIO side. You have to have this in, out, and output enable route all the way through to the throughout the entirety of thing per pin on your peripherals. And then we went over that the Namigen contributes the ultimately the ls180.v is compiled to Verilog, and LTX Peripheral System generates the fabric where the LibreSOC ls180 is a component connected to that fabric. And then you can make the choice to either compile it to FPGA, where the tools will take care of connecting in. Yosis will take care of introducing you to the ECP5 cells, and on the ASIC side, Yosis will take care of introducing the cell library, the standard cell library. And by the way, this is where we introduced the black box PLL and the black box 4K SRAM cell at this point. And then told Alliance Coriolis 2 was told about those as well, so that it could actually do the place and route of those 4K SRAM and the PLL cells, which is these tiny little diagrams here, which you can see. You can see them here at this point. This is at the top left, along the top. There's the 4K SRAMs. In that tiny block in the top right-hand corner is the PLL, which was automatically placed, manually placed, and so were those 4K SRAMs, followed by automatically place and route of the rest of the 130,000 standard cells. So with that in mind, let's do a dive into the source code. So the first thing I want to show you here is the pins, the pin banks. All right. So this is one of the auto-generated outputs from the PenMarks program, which is very useful to be able to review. Have I got the positions of the the power and ground right? Are they properly balanced and distributed throughout, and so on? Then that's also that then these pin numbers and positions then match up directly with these with the information here. Bear in mind, both these outputs, this Markdown file and this SVG image, were auto-generated from the same program. And that program is here. LibreSOC.org Git repositories, the PenMarks repository, source/ls180.py. And here you can see that we've defined the pin banks. There are 32 pins on each side, north, east, south, and west here. And then we define that we actually want on the west side, starting at pin 0, we want 15 pins. So I want 6 pins of the SDRAM, which turns out to be address lines 4 to 9. Likewise, then that gets split up here. There's a second split of another chunk of those things. We should actually be able to trace those through. So let's have a look at the west side here. North, east, south, west. Oh yes, look. These ones here. Whoops. That is 6 address lines, 84 down to 89 in reverse. Reverse order, because otherwise it would go 4, 5, 6, 7, 8, 9 there. And likewise, you can see these ones here, which go from those. How many did it ask for? 15 pins, starting at number 10, west 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops. You get the idea. Oh wait, I know it's from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. Yeah, starting from here. All right. So because they're in reverse order, it goes from that one backwards. Anyway, you get the general idea. So this program, software engineer, remember, this program auto-generates a JSON file. That JSON file is picked up by other programs, including the LTX and including the JTAG boundary scan, and including Coriolis 2. Okay. So let's have a look now at this is the LS180. This is our integration with LibreSOC and LTX. Now, LTX is primarily designed for FPGAs. So let's focus explicitly on the DDR memory interface, the SDR as it's called, right? here is the ECP5, lattice ECP5 DDR5. So it contains the pins, it contains the, it takes care of the clock, etc., etc. Because remember that the ACP5 has an onboard built-in DDR5, right? Or you can use it to do a DDR3 PHY. So you need to have some way to set up the PLL, so that it, etc., etc., etc. And you also need to have some memory registers so that you can then program that PHY via a DFI, standard DFI interface. Okay. At the pads, once you get outside, and here's the pad list for standard standard DRAM: read address strobe, bank address, address line, chip select, reset, clock enable, on die termination, and the pads and things. But the thing is that once you have connected to, and you need to you need to tell the bit stream, XPR AC5, how to connect and what to connect to. But once you have connected, said what the connections are, it ends there. Okay, right. So those three wires, if you have an I/O wire, which you will for the data, because that is both input and output. DQ, here we go. Output enable, DQS output enable. So it's directional, it's bidirectional. Once you have that output, you no longer need to track or trace through anything beyond that point. It goes into, as far as you're concerned, a black box. For the ASIC, on the other hand, you are directly responsible for routing the netlist through to the DDR, to the DRAM memory, the address line or the data line, the data pad for D0, the data pad for D1, the data pad for D2. And consequently, you need a completely different type of specification for a DRAM PHY, because it needs to route those three things. But worse than that, there is a completely separate thing from the pads. The set pads, remember, are separated. Back at this diagram, the LiteX normally would connect these directly from here to here, from the LiteX things to the IO pads. But in our case, because we're doing a boundary scan and we want that boundary scan to include being able to test the DRAM PHY pads independently of LiteX and the test issuer core, we need to separate that. And so this is why back in here we have our own PHY class, which is pretty much a direct copy of the standard generic SDR PHY. Right, this is pretty much exactly the same code, but here we have these are things. This class is the reason why we had to do this, because we need in the LiteX code, it assumes that it's buried in that SDR output class. The input, output, and output enable are buried in that class, whereas we need access to, having put those the information into the SDR output class, we then need to get at it. To think. So this is why we had to write our own PHYs, which specifically understand the context of ASIC, not an assumption that it's going to be taken over by FPGA transparent opaque block, as far as we're concerned. Now, if we have a search for Gen SDR PHY in here, this is the Gen SDR PHY instance. Right. So the way that the LiteX works as far as an SDR, a DRAM thing is concerned, is that because there are so many different types of DDR memory, they have gone ahead and cleanly separated the PHY from the PHY, how it accesses the I/O and manages the PLL, from the rest of the code, and so consequently you can't pass in the SDR PHY class to the add SDRAM function, LiteX function, and it will connect those and wire those two up for you. Right. Things were a little bit different for the rest of the peripherals. The only other peripheral in LiteX which handles it that way is the SDMMC. We had to actually remove the SDMMC because it was SD card, because it was too big to go into the ASIC. But we're still left with that one. Now, in all of the other cases, unfortunately, what we had to do was things like the UART PHY here, and the GPIO, and the SPI interfaces. None of those were designed similarly to abstract out, so we had to literally take a copy of the standard SPI master and GPIO tri-state classes in LiteX and adapt them and just do pretty much a global search and replace substitution, getting those to understand the fact that we needed these triple I/O in, out, and output enable pins to become both in to the things and then come back out again from these class instances, these modules, such that on extraction, so extracting the outputs, we could then connect them to the Corona through the through Coriolis 2. And it's where the difference then is that the FPGA, it's a black box. You hand those the triple in, out, and output enable to the black box of the FPGA resource, and you never see it again. Now, here what we also had to do, this is particularly obtuse, is no, not that one. Is we actually had to have an allocator which duplicated, and that comes back to here. These pin pads inside LiteX, we had to make a separate set and a platform resource which had one set which we called core, because it went to the core. Ultimately, it went through to the code inside test issuer, and the other one was the standard I/O pads. And let me just track that thing. LibreSOC LS180. So here we define the platform. So these are the resources. This is the I/O resources that are available. Clock and reset, JTAG, I2C, SPI, SD card, SDRAM. We actually had to allocate a new set of those via a platform, a constraint manager, a LiteX constraint manager, which was if you look closely inside LiteX, you will find that it already allocates an I/O. There's that I/O, so the pad resources, and that is a separate resource from the one that LiteX normally allocates. Here is our pin specs thing, which reads the JSON file, sets up some pins, and then enumerates all of them and creates that JTAG boundary scan on a pair, on a per pin basis, it creates a pair of these two, of the pin that as to connected to LTX and a pin as to be connected to the I/O pad. And then, unlike a normal LTX thing where you would just pass that platform resource with the pin definition to LTX and it would just get on with it, we need to pass one of those set of pads, and I'm just trying to find it here. You pass one of the set of I/O pads. Here you go, CPU pads. So that's for the DRAM. So you pass the CPU pads to the DRAM PHY, but further down, where is it? Behind the scenes here, when add SDRAM, the add SDRAM, which is a standard function, will get the standard LTX I/O things, and they are not actually connected. So normally you would pass that through thing, and it would be a direct connection between the I/O pads and here. So to get that to happen, you would back here, where was it again? Oh yes, it's already highlighted. You would not pass self.cpu.cpu pads to the thing. You would pass the self.cpu.io pads thing to the SDR PHY, and that would bypass. Unfortunately, that would, being the standard way that LTX is used, that would completely bypass the JTAG boundary scan. Consequently, that would make our chip untestable. So we don't want to do that. So anyway, we had to do exactly the same thing for the GPIO, for the UART, absolutely every peripheral. The only ones that we did not do that for was for JTAG itself. So JTAG doesn't try and boundary scan itself. One other thing, by the way, you will know that an FPGA itself has a JTAG interface on it. But that JTAG interface, it is completely separate. So we actually had to have some code, and I'm going to see if I can C4M JTAG. Yeah, here we go. So this was the code that we used from Chips for Makers, and it actually implements a fully functioning JTAG tap interface. So it supports the full JTAG finite state machine of being able to support TDI, TDO, and so on. But what's really nice about it is that you can add these buses, and you can add the JTAG boundary scan I/O that you need, and you can add a wishbone interface, and if you want to shift register for anything else, you can do so. It's extremely smart. So basically, over JTAG, with this wishbone interface thing, we can actually control access the memory through JTAG, and it will it's standard thing. It's really very, very cool. So let's have a look at what else we've got. So we've got that PenMarks. Here's the pen class. Now this was picked up in two places. So remember, this reads the JSON file. That JSON file contains the pin definitions. So it's passed in here as a pin set. It's just a Python dictionary. And that creates this class pins, creates this boundary scan, the I/O types of whether it's an input, an output, or a bidirectional or a tri-stated. Here's your different types that you can have: in, out, tri-stated output, in, out, tri-stated. there we go. Add the I/O. This is creating the boundary scan for you, which you can then do in your ASIC. And you wouldn't have this normally in an FPGA anyway, because why would you need it? You know, the FPGA's I/O is assumed to be reliable. It was tested at the factory. Whereas but here, you can't get away with that. So this is another reason I think you have to have a boundary scan check and thing on for an ASIC, because otherwise you don't know which bit is broken. The I/O pad itself, or the peripheral connectivity driving that I/O pad. So now this is test issuer, and test issuer here again, it picks up the pin specs. Again, remember, this is the exact same function that we used in the LTX thing. So this is why it's so important to make sure that you don't end up duplicating this information and maintaining it in 4 different places and getting it wrong. So for get underscore pin specs, turn, there we go, and that gets passed to the JTAG instance, and behind that JTAG instance will be the DMI interface as well. So we also added, via the JTAG interface, we added the ability to disable the instruction wishbone interface. Just disconnect it completely in case there's a fault in the ASIC when it comes back. The wishbone peripheral connection is faulty. Maybe a short circuit or something like that. Also to disconnect the data things, and to disconnect the 4K SRAMs. Normally what you do is you'd have completely separate power lines for each of those things, and then they would just become a big resistor. But a tri-stated big resistor, but we decided not to do that because it would complicate the power provision to the chip. So we only have 2 rings, a 3.3 volt ring for I/O and a 1.8 ring for the main core. So here you can see we're adding those black box cells, the 4K SRAMs. That's the ZIX interface for interrupt controller. That's a test thing. That's our big main power decoder 2. The source goes online. You can go through it. It's divided up thing. It's pretty readable in comments. There's a fetch, a finite state machine, an issue finite state machine, an execute one, and where's the other one? DMI interface thing. Oh, and the TBN deck is its own separate finite state machine, which monitors the control signals coming from the thing. So it only goes ahead and executes the deck and TB finite state machine in between the cycles of the main core one, and that comes back to here. So that's what we're going over there. All right, where are we? Yeah. So this is the function which actually picks up the JSON file and is used by the rest of the code. And this is also used in the Coriolis 2. This exact same code is in the Coriolis 2 thing for it to pick up the exact same JSON file and create the corona. And that corona was this ring here. Can you see there's some lines here? I know those are the I/O pads themselves, but on the inside there's a ring, a thing, and that the positioning of these pads are what the specification was done, which was back in that pinouts program. So it's all computer controls. There is no manual steps involved here. It's quite quite specific. But yeah, so I think we're good there. So that, yeah, the main things are, you need a boundary scan, and you need the entire code base to understand it, and it routes right the way through pretty much absolutely everything. It needs to be in terms of the 3 pins. To each of the I/O pads goes 3 wires, apart from power and ground, of course. The input, output, and output enable. And the difference here there with an FPGA is that that's a black box, where the tools, Next PNR ECP5, the place and route tool, doesn't need to know about that, doesn't need to route that back out for you, but instead it sort of disappears into a black box resource defined by the manufacturer of the FPGA. And likewise, you get a different cell library, in effect, which so the YOSIS routing program understands that you have a LUT for cells, BRAM cells, DSP cells, GPIO cells, PLL cells, which it is designed to rewrite the BLF file to correspond to those resources, and that's then picked up by the Next PNR ECP5 tool. Whereas for the ASIC, there's a completely different set of cells: MUX cell, DFF cell, XOR, NAND, NOT buffer, etc., etc. And even massive things like PLL cell and 4K SRAM cell, you can tell it by marking those as black box, to tell YOSIS, I'm going to deal with this, I've defined this, please don't try and replace it with something in terms of the standard cells, which we had quite a bit of a fight with YOSIS over getting it to do that, because if we had not marked the 4K SRAM as a black box cell, then what YOSIS would have done was it would have gone, oh, this 4K SRAM is an SRAM, I don't understand memory cells, so I'm going to create a massive set of flip-flops for you, which would have been 5 times bigger than the actual, no, about 10 times bigger than the actual chip. As flip-flops are extraordinarily inefficient way of doing things, but they're very, very fast. So you need them in some circumstances, but because the 4K SRAMs are so big, there's no way that we could do that, or we couldn't let YOSIS do it, and so had to tell it, treat this as a black box, please. It will be defined by the ASIC designer, who will provide us with a 4K SRAM cell, which then Coriolis 2 is told about and places and then routes the connections to it, and likewise for the PLL. So yeah, I think we're good there. Thank you very much. Questions, and if anybody has any questions beyond these things, you can contact us on the mailing list. LibreSOC Dev, here we go. So more information about this list here, right? And you can also contact us on IRC, and you can see the IRC logs here, discussions and so on. It's a Libre project. This is what you get. So yeah, thank you very much.